so I hope you can all hear and see me now. I must say that I'm very happy that even though we are locked in formally by means of this virtual seminar, we can reach out to so many people and get into contact, and it's really wonderful. And I hope that not only you who are sitting in front of your computers today, but also your friends and family are all safe and well. Okay, so what I want to talk about is a very classical topic, and the origins of this is the Custon-Warner problem of prescribed curvature on a closed two-dimensional manifold, closed Riemann surface. So M is my symbol for this surface, and GB is the background metric. And then we let F be a smooth function given on M. And we want to find conformal metrics, that is metrics G equal e to the 2u times the background metric, having Gauss curvature equal to F. And there's a formula for the Gauss curvature in terms of the function u, which I've written down here. So then if we look at the example when M is the flat torus with background curvature 0, the problem is equivalent to find a solution for a given F to the partial differential equation 1 that's displayed here. So simply, you want to solve minus Laplacian u equal F times e to the 2u on the torus. Now, Custon-Warner already in the 70s noticed that there are conditions that are both necessary and sufficient for the solvability of 1, which is the condition stated in the following theorem. So there exists a solution to equation 1 if and only if the integral of the given function with respect to the background metric is negative, and if the function f is sign changing. So the supremum of f has to be strictly positive for this. And this condition now invites to construct examples where you can check this condition very easily. So for instance, if we take a function f0 that's smooth, non-positive, and with maximum equal to 0, and non-constant, and then if we lift up the function f by adding positive number lambda to it, to obtain these functions f lambda equal f0 plus lambda, then there is a number lambda 0 positive, such that for any lambda between 0 and lambda 0, the necessary and sufficient condition of Custon-Warner is satisfied. So there exists a solution u lambda to the equation 1 upstairs. And however, when lambda tends to 0, the solution u lambda to this equation has to blow up, because when lambda equals 0, there is no solution, because this strict inequality on the right-hand side in the Custon-Warner theorem no longer is satisfied. And a similar phenomenon occurs for higher genus. So when the Euler characteristic of the surface M is negative, and when we endow it with the background curvature, background metric of constant curvature -1, then there are unstable solutions u lambda, which are characterized as minimax for corresponding variational problem, that blow up as lambda tends to 0. So this these large solutions that blow up as lambda tends to 0 in higher genus were discovered by Ding Liu in 1995. So on the next page, let me show you the situation graphically. So here I summarize the analytic conditions. Chi-M is non-positive, F0 is non-positive with maximum equal to 0, and F lambda is this shifted function. then you have for lambda positive but not too big, you have these solutions u lambda that blow up as lambda tends to 0. And the graphs of where I plot the L infinity norm of the solutions versus the parameter lambda, they may look like this in the case of the torus. So there's possibly only one branch. And for homogeneous surfaces, you have here a branch of stable solutions to the prescribed curvature equation that then is met by a branch of unstable solutions that explode as lambda tends to 0. But from these existence results, which are only qualitative, you cannot say anything about the shape of these large solutions and the corresponding metrics. However, recently, by using the monotonicity trick that I found in 1987-88, we were able to analyze the blow-up in a certain number of cases. First, jointly with Francisca Bora and Luca Galimberti in 2013, respectively 2015, we looked at the homogeneous case. And then Luca Galimberti in 2015 looked at the torus. And we again assume that f0 is a non-positive function with maximum value 0. And we suppose that all the maximum points are non-degenerate. Then, for a certain sequence of parameters lambda k converging down to 0, the corresponding solutions uk equal u lambda k, satisfying the prescribed curvature, may blow up at a finite number of points, pi infinity, which necessarily are maximum points of the given function f0. And moreover, by the monotonicity trick, you have bounds for the total curvature of the induced matrix, and you can prove the following convergence result. So there are, for each I between 1 and I0, there are radii rki tending to 0 and constant cky tending to infinity, such that if you rescale the solutions uk with the radii rki and subtract cky, then the resulting functions wki converge smoothly locally on R2 to a limit wi infinity, which is bounded from above, and which either induces a spherical metric of Gauss curvature equal to 1, or in the second case, induces a metric of curvature given by the second order expansion of the given function f0 around the point, the limit point pi infinity, which is therefore of the form k gi infinity equal 1 plus ax comma x, where a is proportional to the Hessian of f0 at the limit point pi infinity. And since we assume that these critical points, the maximum points, are all non-degenerate, this is a strictly negative definite matrix, and the induced metrics all have finite volume and finite total curvature. Now, of course, you may wonder which of these cases happens. And in 2017, I was able to resolve this question by showing that all bubbles must be spherical. So only the case A can occur in the preceding theorem. And this is, in fact, in agreement with a result by Del Pino and Roman, who obtained in 2015 branches of bubbling metrics that exhibit spherical bubbling at any collection of maximum points. So there are possibly multiple solutions that blow up as lambda tends to 0, but they all exhibit only spherical bubbling in this work that Delphine Roman produced. And it's expected to have similar results for the torus, but I'm not aware of any published result for this case. But anyway, this nice coincidence of this theorem that I proved in 2017 with these constructions leads to the conjecture that perhaps all solutions that blow up are spherical or exhibit spherical blow-up in the sense of the previous result. Now, then there was the question whether this was special to 2 dimensions or whether it can also occur, this phenomenon can also be demonstrated in higher dimensions. For instance, for the problem of prescribed Q curvature on a 4-manifold. And let me talk now about the analogous situation for that setting. So this is then again the case of the torus that we want to look at with a flat background metric where the Q curvature then is 0. And given f, the equation that we want to solve then is very similar to the equation that we've seen before, only now the operator is 4th order, it's delta squared acting on u, and right-hand side f times e to the 4u. So there are results which are very similar to the Carsten-Warner result due to Ge and Hsu from 2008. And namely, they showed that if the average of f is strictly negative and if f is sign changing, then you can find a solution to this equation 3. However, this is no longer an equivalence. The condition is no longer necessary, but you can only conclude from the existence of a solution that f must change sign. However, that's enough to play the same game as we played before in the 2-dimensional case. We can take any function f0, which is non-positive and has maximum 0, and add a positive number lambda to it to achieve the sufficient condition in the Ge-Hsu theorem. And then we find u lambda solving the equation 3 for a range of lambdas between 0 and some constant lambda 0. And moreover, since necessarily for the existence of a solution to 3, f has to change sign, we conclude again that as lambda tends to 0, the solutions u lambda have to blow up. And there's the question how they blow up. First of all, Guo Zhang in 2019 were able to use the monotonicity trick in a manner similar to the way that Bora, Galimberti, and I used it to obtain a blow-up result in the spirit of what we had seen in the first theorem. And in fact, it will be important for the later part of the talk to note that similar results also will hold in the degenerate case when the function f0 only takes off to 4th order from a constant. Well, the Guo-Zhang result for the 4th order case leaves open the possibility whether you always have spherical blow up or whether you can have some other kind of blow up with a function k equal 1 plus a x comma x or a different perturbation term resulting from the jet of the function f0 at the critical point. And therefore, we now want to ask the question whether the bubbles, also in 4 dimensions, always are spherical. This is not obvious because in 4 dimensions, there are exotic bubbles that were discovered by C.S. Lin in 1998. He, in fact, constructed radially symmetric solutions of the prescribed Q curvature equation for Q curvature f equal 1 that have a certain asymptotic behavior for the Laplacian, and therefore give rise to tear-shaped metrics. So they don't close up as round spherical metrics, but they have kind of a cusp at infinity. So this is one class of exotic solutions. There are other solutions with non-constant Q curvature on R4 discovered by Chang and Chen in 2001. So they constructed solutions to the prescribed Q curvature equation on R4 for any smooth function f which is positive somewhere and decays to some polynomial power x to the minus s with a positive or x to the s with a negative exponent s. However, in the case of Blowup, by a result that I obtained with Frédéric Robert in 2004, there's an additional condition working for us, namely, for any bubble metric resulting from Blowup, necessarily the Laplacian decays to 0 as x tends to infinity. So because of the different asymptotic behavior in C.S. Lean's result, these exotic metrics would then be ruled out. All right, so let's come now to the result that I want to talk about. We will be looking at the degenerate case that I briefly described just a moment ago. And M is the 4 torus, F0 is non-positive with maximum equal to 0, smooth, non-constant. And we'll assume that we have a sequence of bubbling solutions, UK blowing up at a point P0, where F0 and its first derivatives up to the third derivatives all vanish, while the fourth derivative is negative definite for linear form. So in that setting, we can expect to have a blow-up limit W, which is bounded from above, and which either induces a spherical metric of constant Q curvature on R4, or induces a metric of Q curvature given by Kg equal 1 plus A fourth order for linear form coming from the fourth order derivatives of F0 at the blow-up point. And as in the two-dimensional case, the blow-up metrics always have finite volume and finite total curvature. So I'll denote the volume by V0 and the total curvature by K0. And now, just as in the two, and oh, I should not forget the asymptotic condition coming from my result with Frédéric Robert, the Laplacian of W tends to 0 at infinity. So what I want to talk about is this Liouville-type result. And just like in the two-dimensional case, in this degenerate setting where the blown up curvature is 1 plus A, this 4 linear form, which is negative, definite, and symmetric, then I prove that there is no solution of this prescribed Q curvature equation for this curvature which is bounded from above and satisfies the asymptotic condition Laplacian U of x tends to 0 as x tends to infinity, inducing a metric of finite volume and finite curvature, so that only the spherical blow-up is possible, just like in the two-dimensional setting. Of course, this result is not completely satisfying because we're doing something very special. We're not looking at and in particular, not looking at the non-degenerate case, which we would think would be the generic one. And it's actually an open question whether similar results will hold in that case. And you'll see where the proof makes special use of this shape of the curvature term. All right, so let me tell you a little bit about the details, how we prove this result. So we argue by contradiction, and we assume that there is a solution with the properties of the theorem for the prescribed curvature function k equal 1 plus a of x comma x. And the first step is to derive a representation formula analogous to what Zhang-Shu Lin did in his work in 1998. Namely, we can take the fundamental solution to the bilaplacian and form this expression, which then defines a solution to the equation bilaplacian v equal f. So then we have two solutions, u and f, solving bilaplacian u equal f equal bilaplacian v, which means that the difference Laplacian u minus Laplacian v is a harmonic function. And on the other hand, the mean value of h on any ball of radius 1 centered at a point x0, by our assumptions on u and the formula for v, can be estimated as follows. First of all, Laplacian u of x tends to 0 as x tends to infinity. So Laplacian u will contribute this small error. On the other hand, we can compute directly from the formula Laplacian of v. And even though there is a singular integral involved here, when we take the average over a ball around point x0 in x, then this singularity is smoothed out. And because f has a finite integral, then also the second term will converge to 0 as x tends to infinity. And since h is harmonic, h is given by the mean value on any ball. And since the integral on any ball tends to 0 as x0 tends to infinity, h will converge to 0 at infinity and therefore will vanish identically. But that means that also the function little h, which is the difference of u and v, will be harmonic. And now note that because u is bounded from above and v by the formula, which is explicitly here, satisfies the bound v of x is less than a constant times log x for large x. Because of this upper bound for little h, you can conclude that little h must be a constant. For instance, you can look at the mean value estimate for the gradient of little h and then conclude that the gradient has to vanish identically. So that proves this representation formula. And that now has the nice consequence that we can estimate the asymptotic behavior of e to the u. First, we form the quotient u of x by log of norm of x. And then we have this expression from the previous formula. And the constant here will, when we divide by log of norm of x, will converge to 0. And in this expression, the factor in front of the f will converge to 1. So we converge to 1 over 8 pi squared times the integral of f, which was the total curvature. So the result is this number, which I call alpha, or minus alpha, and u of x divided by log norm of x converges to this limit as x tends to infinity. So therefore, e to the u behaves like x to the minus alpha. And then for any number mu larger than 4 alpha minus 4, we can bound the power x to the minus u by x to the 4 for this minus 4 times e to the 4u for the 4 alpha. And this integral then can be bounded by a constant times x to the 4 times e to the 4u dx plus a constant. But x to the 4 is bounded by our multilinear expression a of 4 times x. And this multilinear expression occurs in the curvature. So I only have to add and subtract 1 in here to produce the total curvature, and the one that I have to add will give us the volume V0. So this expression here is finite, and therefore this is finite. But mu may be any number which is strictly larger than this, and therefore, because finiteness of this integral requires mu to be larger than 4, therefore we conclude that alpha has to be at least equal to 2. And that means, by the definition of alpha, that the total curvature K0, which is equal to 8 pi squared times alpha, has to be at least 16 pi squared and is positive. So that is one estimate. And this is actually the part of the argument where this type of behavior of the curvature function enters. The next part is a simple, technical step using the Pohojayev identity. So we multiply both terms of our equation with the multiplier x dot gradient u, responsible for scaling. And then miraculously, we come up for the product with a divergence expression. So it is this long expression that we can compute from this trick. And on the other hand, remember that by Laplacian u was f of x, and f of x was k times e to the u. So on the other hand, we have the following expression for this when we look at the right-hand side. Namely, this is 1 plus the multilinear term a times e to the 4u times x dot gradient u. And this again can be partially interpreted as a divergence. So we write it as a divergence, and we discover this term here when the divergence falls on the exponential factor. But there are further terms that result when we differentiate in x and when we differentiate a. And if we sort out the various terms, then we see this expression coming up, which when integrated will give us the total curvature. And in order to produce this number 1 here with a factor 2, we had only 1 there. We also have to introduce the volume term, which comes when we integrate e to the 4u. So we now do this integration, and we observe that by finiteness of the integral of f, the divergence term here drops out when we integrate over a suitable collection of balls BR around 0 for suitable radii tending to infinity. And therefore, for suitable r tending to infinity, also the integral of the left-hand side over ball BR, which is equal to the integral of the right-hand side over the ball BR, will tend to the limit V0, which is the integral of e to the 4u, minus 2k0, which is the integral of this term. All right, so we're almost done, because we can also now look in more detail on the left-hand side. So now we look at the bilaplacian of u times the scaling multiplier, and we had rewritten that as a divergence term. So when we integrate over the ball BR, all we are left with is this boundary integral term. And even though these terms look horrible, and indeed they are, just like in my paper in 2017, we can estimate these terms one by one and find that this expression here converges to minus 1 over 16 pi squared k0 squared as r tends to infinity. So now, when we combine this convergence result with what we already know, then we obtain the following chain of inequalities. First, from one of the first slides of the proof, we had this lower bound for k0. K0 was bounded from below by 16 pi squared. And this is where the shape of the curvature function entered, where it played a role that we were looking at this degenerate case. Then necessarily k0 is at most equal to v0, because k0 and v0 differ by a negative term. And then we can, from the previous slide, we can identify v0 with 2k0 plus the integral of this term. So the integral of this term converges to minus 1 over 16 pi squared k0 squared. So this is what we get from this previous convergence result. And now all we have to do is write this over one denominator. And then we observe that since k0 is at least 16 pi squared, in fact, k0 has to be equal 16 pi squared in order for this inequality to still hold true. Otherwise, this factor would be strictly less than 1, and therefore this term on the right could not be bigger than k0. So we conclude that k0 is 16 pi squared, but then also this inequality has to be an identity, and therefore k0 is equal to v0, which is then the desired contradiction, because if the A term is present, k0 has to be strictly less than v0. So the proof of the theorem is complete. Well, one may ask if this argument only works in the degenerate case. I mean, there's this crucial step 5, which is necessary for us in order to arrive at this conclusion, but maybe there is a different proof that can circumvent the assumption about the term k. So this, by the way, also is an interesting open question in the two-dimensional case. Can one extend the argument proving sphericity of the blow-up solutions in 2 dimensions to more general functions f0 with degenerate or non-degenerate critical points? So this is one big open question that I would like to pose to you. And moreover, does the argument that I presented to you in 4 space dimensions, does it stop there, or can one extend the result to higher dimensions still when n is equal to m strictly larger than 4? So since we're locked down, probably still for a little while, I hope that I've given you some material to think about and possibly come up with new arguments and new ideas to expand our knowledge about prescribed curvature equations. Thank you very much for your attention.